Hello everyone. Today I am going to make a audio recording for visually impaired student of inorganic chemistry for BSc second year and its writer is SP Jauhar from Modern Publication and name of the chapter is Acid and Base. Introduction. Acid and base are so frequent in chemistry that these have been defined many times in various ways. The earliest definitions were based mainly on observable properties such as their taste and their effect on litmus. Their acids were defined as those substances which contain hydrogen as an essential constituent and have show test turn blue litmus paper red, react with metal to liberate hydrogen and conduct electricity. On the other hand, bases are defined as substances which react with acid to form salt and exhibit bitter test turn red litmus paper blue and conduct electricity. However, these definitions now are the historical interest only. A number of concepts of acid and bases such as Arrhenius concept, Lowry and Bronsted concept, Lewis concept, and Lux fluid concept have been introduced and are discussed in this chapter. 7.2 Arrhenius concept. Arrhenius concept of acid and bases deals in aqueous solutions. According to this solution concept, an acid is a substance which gives as positive ion in aqueous solution. A base is a substance which gives OH ions in aqueous solution. HCl in aqueous solution as positive and Cl negative. Neutralization is defined as the combination of H positive ion from the acid and OH negative ions from the base to form u- un- unionized water. Limitation of Arrhenius theory. Arrhenius concept of acid and base remain widely used for quite a long time. However, there are certain limitations of this definition which are discussed below. First, nature of the hydrogen ion. According to Arrhenius concept, acids are substances capable of furnishing H positive ions in water. H positive ion does not exist freely and combine with water to form hydronium ion. Thus, it is hydronium ion and not the free H positive ion in water which is responsible for the acidic behavior of substances. Number 2. Limited scope. Arrhenius concept of acid and base is limited to aqueous medium only. It fails to explain the acid or base behavior in non-aqueous medium such as ammonia, alcohol, or sulfur dioxide. Number 3. Acid and base without H positive and OH negative. There are a number of substances such as CO2, SO2 which do not have any H positive ion but behave in acid. Similarly, compounds like CaO, MgO, anhydrous NH3, Na2O3, CO3 which do not contain OH negative still behave as base. Number 4. Neutralization without H positive and OH ions. Neutralization between HCl and NH3 does not involve H positive and OH ions. Bronsted Lowry concept of acid and bases. In order to overcome the shortcoming of Arrhenius concept, Bronsted and Lowry independently and in 1923 put forward a more general concept for acid and bases. This concept is called Bronsted-Lowry concept of acid and base. According to this concept, an acid is a substance which has a tendency to donate a proton, and base is a substance which has tendency to accept a proton. In other way, in an acid is a proton donor and base is proton acceptor. In fact, acid base reactions involves transfer of proton from an acid to a base. This is why this concept is also called proton transfer concept of acid and base. And acid or base may be molecular and ionic species. Molecular acid HF, HCl, HNO3, H2SO4, CH3, CuWH, H2S, H2O2, H3PO4, extra ionic acids, hydronium ions, ammonium HSO4, HCO3, negative extra molecular base H2O, NH3, R, NH2, R2 NH extra. Ionic bases OH negative, S2 negative, CO3 2 negatives, chlorine negative, bromine negative extra. It is important to note that no single substance is an acid or base. In other words, a single substance cannot donate a proton unless some other substance which concept the accept the proton is also present. For example, HCl is an acid in aqueous solution because HCl donate a proton and water accept it. It may also be noted that the transfer of proton can take place even in the absence of a solvent. For example, the reaction between gases ammonia and gases hydrogen chloride involves an acid-base reaction as NH3 plus HCl NH4Cl. In this example, HCl has donated a proton and ammonia has accepted it. Hence, HCl is an acid while ammonia is a base. Some other example of acid-base reaction according to Lowry-Bronsted concept are HCl plus H2O product H3O positive and Cl negative ions. A careful study of the above equation reveals that water is an acid with respect to ammonia, whereas it is a base with respect to hydrochloric acid, such as substance like H2O. This act as an acid proton donor as well as a base proton acceptor is called an hem- amphoteric and amphiprotic substance. Other similar example of amphoteric substance are HSO4 and H3 HCO3 negative. Conjugate acid base pair. When an acid loses a proton, the residue part part of it will have a tendency to accept the proton, therefore it will behave as a base. In terms of a definition, acid and base are interrelated as acid, proton, and plus base. The acid and the base which differ by proton are known as conjugate acid base pair. Consider a dissociation of acetic acid in water which may be represented as acid plus base acid plus base. In the forward reaction from left to right, acidic acid donate a proton and to water and thus act as an acid. Water in turn accept a proton and therefore act as a base. Similarly, in the backward reaction, hydronium ion donate a proton to to the acetate ion and therefore behave as an acid. The acetate ion in turn accept a proton and therefore behave as a base. Such pair of substances which can be formed from one another by the gain or loss of proton are known as conjugate acid-base pairs. Thus, in the above example, acetic ion is conjugate acid of acetate ion and acetate ion is the conjugate base of the acetic acid. Similarly, water is the conjugate base of the hydronium ion and hydronium ion is a conjugate acid of water. The use of few examples may be helpful to isolate the concept of conjugate acid and conjugate base. Comparison with Arrhenius concept it is important to point out here that both Arrhenius concept as well as Bronsted concept require an acid to be a source of proton. The sole Arrhenius acids are Bronsted acids. Number two, all Bronsted base may not be Arrhenius base. According to Arrhenius, a base furnish OH negative ions in the solution. According to Bronson, in base is a proton acceptor as CO3 2 negative ion cannot furnish OH negative ion in aqueous solution. Therefore, according to Arrhenius concept, it does not act as a base. Conclusion: all Bronsted bases are not Arrhenius base, whereas all Arrhenius acids are Bronsted acids. Relative strength of acid and base. According to a Lowry concept, the strength of an acid depend upon its tendency to donate a proton, while the strength of a base depend upon its tendency to accept a proton. An acid which has a strong tendency to give proton is called strong acid. Similarly, base which has a strong tendency to accept a proton is called a strong base. Strong acid has a weak conjugate base HCl plus H2O product S3O positive plus Cl negative weak base. HCl has a greater tendency to lose a proton and therefore equilibrium shifts more toward the right. Its conjugate base Cl negative ion has a little tendency to accept a proton and thus act as a weak base. Strong acid weak conjugate base plus H positive. A weak acid has a strong conjugate base. Acetic acid has a lesser tendency to donate a proton and therefore equilibrium shift more toward left. Its conjugate base CH3COOH ion has a greater tendency to accept a proton and thus act as a strong base. Weak acid equilibrium H positive plus strong conjugate base. Thus it follows a strong acid has a weak conjugate base and a weak acid base has a strong conjugate base. The same is true for bases. Water is very weak acid because its conjugate base hydrogen hydroxide ion it he is a strong base. At the same time, water is very weak base because its conjugate acid hydronium ion H3O positive is cold is very strong acid. Limitation of Bronsted Lowry concept. Although Although Bronsted Lowry concept is a modification of Arrhenius theory, yet it failed to explain some of the well-known reactions. For example, it cannot explain first acidic oxides such as anhydrous carbon oxide, dioxide, sulfur dioxide, and sulfur trioxide, etc., which do not have contain hydrogen at all but can act as acid and neutralize bases oxide like calcium oxide and barium oxide even in the absence of substance. Number two, it failed to explain the acidic nature of compounds such as BF3, AlCl3. Solvent system concept of acid and base. Solvent system concept of acid and base is an extension of the Lowry Bronsted concept of both protonic and non-protonic solvent. A protonic solvent contains a proton, while a non-protonic solvent is that which does not contain any proton. According to solvent system introduced by KD and LC in 1928, an acid is a substance which either by direct dissociation or by the interaction with the solvent gives a cation characteristic of the solvent. For example, HCl behave as an acid in water solvent as it gives the cation characteristic of water. A base is a substance which either by direct dissociation or by interaction with the solvent gives rise to an anion characteristic of the solvent. It is interesting to note that acetic acid behave as an acid in water as it produces the cation characteristic of water. Acetic acid behave as a base in sulfuric acid as it produces the anion characteristic of sulfuric acid. Similarly, urea is water is neutral while is liquid ammonia it behave as an acid as it produces the cation characteristic of ammonia. Neutralization. According to solvent system concept, neutralization is the combination of solvent cation and solvent anion to produce the solvent. Lewis concept of acid and base. Another more general definition of acid and base was proposed in 1923 by Z. and Lewis. According to Lewis, an acid is a base is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons to form a coordinate or deviate bond. In other words, while an acid is an electron pair acceptor, a base is electron pair donor. Accord- an acid needs not certain hydrogen. Actually, any substance which has an empty orbital to accommodate a pair of electrons can act as a Lewis acid, while any substance with unshared pair of electrons in the outer energy level can act as a Lewis base. Lewis acid can be of the following type. First, molecules having an atom with incomplete octet. BF3 AlCl3 are example of this type as so note that the central atom boron and aluminium have only 6 electrons. First, second, simple cation. All cation in general and are strong Lewis because they are already deficient of electron, while large size cations such as Na positive, K positive, Ca2 positive, etc. behave as weak Lewis acid. Small size cation has H positive, Ag positive behave as strong Lewis acid. The molecules in which the central atom has available d orbital may acquire more than 8 valence electrons, as that is SiF F4 and SnCl4 behave as Lewis acid as silicon and tin can extend their covalency from 4 to 6. SiF4 plus 2F Lewis acid plus Lewis base complex. Molecules with fourth molecules with a multiple bond between atom or dissimilar electronegativity. CO2 behave as a Lewis acid. It is because the oxygen atom, being more electronegative, has a tendency to attract a shared pair of electrons more toward it. This causes a positive charge on carbon and consequently become deficient in electron and behave as Lewis acid. CO2 behaves similarly as Lewis acid toward OH negative. Lewis base may be any of the following type of substances. Negative ions. All ions are Lewis bases because they are rich of electron pair. Molecules with one or more than one unshared pair of electrons. Neutralization. According to Lewis concept, acid and base neutralization involves the sharing of the electron pair of a base by an acid to form coordinate or David bond. As it may be noted that substance which is capable of donating a pair of electrons, Lewis base, can also act as proton acceptor. Just all bronzed Lowry bases are also Lewis base. However, this is not true in case of acid. For example, HCl can donate a proton but cannot accept an electron pair. Therefore, all bronzed Lowry acid may not be Lewis acid. The Lux fluid definition. Instead of using protons and anion characteristic of solvent, they defined acid and oxide which can accept oxygen, base and oxide which donate oxygen. This system is very useful in dealing with anhydrous reaction is fused melts of oxide and other high temperature reactions such as are found in metallurgy and this theory has an inverse relationship to aqueous chemistry since Lux fluid acid are oxide which react with water giving bases in water and Lux fluid bases react with water giving acid. The USN concept. According to this concept, an acid is a chemical species which react with bases give up cation or accept anion or electrons, and a base is any chemical species which react with acid give as anion or electrons and combine with cations. This is very wide definition and include all the Lewis acid base type of reaction, and in addition in it include redox reaction involving the transfer of electrons. Drawback drawback of Lewis concept. Lewis' approach to acid and base is much more general and provide a clear understanding of many acid-base reactions. Yet it has several drawbacks of as discussed below. First, it is too general and include all reactions involving the formation of coordination compound. As a result, it is not possible to determine the relative strength of acid Lewis acid and bases. 2. Second, it does not explain the behavior of strong protonic acids such as HCl, HNO3, H2SO4, which do not form coordinate bond with bases. These acids therefore do not fit into Lewis concept of acid. Third, acid-base reactions are generally fast and take place almost, but formation of coordination compound is very slow. Lewis theory could not explain this. Fourth, catalytic activity of many acids is due to H positive ions. Since a Lewis acid need to note certain hydrogen, many Lewis acid will not have this catalytic property. Fourth, fifth, it cannot be used for the comparison of the relative strength of acid and base as there is acid and base combined due to the formation of coordinate bond which does not involve complete transfer of electron. Comparative study of acid-base theory. A comparative summary of various theory discussed in the chapter may be summed as follow. Reynolds theory, which is truly only in aqueous solution, define an acid is a substance which is capable of H positive and while a base is a substance which is capable of furnishing OH anion in aqueous solution. Bronzed theory, which is applicable in any solvent, define an acid is a substance which can act as a proton donor, which while a base which can act as a proton acceptor. Lewis theory, which is applicable even without a solvent, define an acid is a substance which can accept a pair of electron, and base is as a substance which can donate a pair of electron. Relative strength of acid and base. When the acid Ha dissociated in water. The following equilibrium is Ha plus H2O equilibrium. H3O positive plus A negative. Acid differ in the extent to which they donate proton to water. In aqueous solution, acid which donate all their proton to water molecule are known as strong acid, and the equilibrium in the above reaction lies in the right. It also implies that the conjugate base of the strong acid is weak and vice versa. On the other hand, if Ha is a weak acid, only a few proton will be donating to water molecules, and the above equilibrium will lie toward the left. Using the idea of an acid as a proton donor and a base is an acceptor, one can arrange all acid and base in the order of their increasing strength. It follows that if an acid is weak, its conjugate base is very strong. This is because it must have a strong affinity for proton. For example, ethanol is a weak acid, but the ethoxide ion is strong base. Similarly, perchloric acid is a very strong acid. Its ion is a very weak base. Acid base reaction competition for proton. Let us consider the reaction acid plus base, acid 1 plus base 2. The above reaction seems to be competition between two bases H2O and Cl for the proton. Water is the stronger base between the two. Therefore, there is also competition between HCl and H3O, which is positive to donate a proton. Since HCl donate the proton in the above reaction, it must be the stronger acid. In general, acid base reaction form the weakest acid and weakest base. It follows then that the strength of an acid or base depend on competition with the other acid or base. The strength of an acid H in water, the extent of which is dissociate, can be determined by considering the equilibrium Ha plus H2O equilibrium H3O positive plus A negative. Effect of solvent leaving effect or differentiating solvent. Solvent play a very important role in determining the acidity and basicity of a substance by a doper choice of the solvent. The apparent acidic and basic property of a substance can be increased or decrease. As an example, hydrogen chloride is strong acid in water while a weak acid in benzene. The effect results from the fact that the strong acid which is available in a given protonic solvent is that which result from the self ionization of solvent. Similarly, the strong base is that which result from the self ionization of a solvent. Let us consider the following auto ionization reaction as 2H2O H3O positive plus OH negative. In aqueous solution, the stronger acid which can exist in the hydronium ion H3O positive. All the mineral acids known as chemists have ex- equal strength in aqueous solution. This is because these acidic such as perchloric acid, hydroic acid, hydrobromic acid, nitric acid, or hydrochloric acid, all the stronger proton donor than in the hydronium ions. All reaction completely with water to produce hydronium ion. Thus, acids stronger than H3O positive are levered to the strength of H3O positive when placed in aqueous solution. Similarly, the very strong bases such as hydride, H negative amide, and NS2 negative and hydroxide ion all react completely in aqueous solution to yield hydroxide ion. It is thus useless to use such strong bases in aqueous solution. This is because all these strong bases are levered to the strength of OH and in reaction with the solvent. This reaction are represented below. It is thus quite clear that the selection of the solvent play a very important role in determining the acidity or basicity of a substance. In the examples cited above, it is clear that water is leaving solvent for acids such as HCl4, Hi, HBr, HNO3, HCl. It is also leaving solvent for bases such as NH, Na, NH2, and NaOC2H5. If we use liquid ammonia as a solvent, even then all acid wise HClO4, Hi, HBr, HNO3, and will be levered to the strength of NH4 negative positive, and this is because all these solids are capable to donating proton completely to liquid ammonia. However, if we use anhydrous acidic acid, it act as a differentiating solvent. This is because acetic acid is relatively a poor proton acceptor. Perchloric acid react completely with acetic acid CH3 COOH plus HClO4 CH3 COOH H2 positive and ClO negative 4 negative, whereas sulfuric, hydrochloric, and other acid behave as a weak electrolyte, that is, do not react completely with the acetic acid. Thus, actually, in acidic acid solvent appear to be a much weaker acid than in water. With the help of conductivity measurement of a mineral acid solution in acidic acid solvent, it can be shown that their strength follow this order. HNO3 is greater is less than HCl, is less than H2SO4, less than HBr, and less than HClO4. Thus, it may be conclude that acidic solvent tends to differentiate between acid and level of the bases, where the basic solvent like ammonia tends to level of acids and differentiate bases. It in fact all acid and base stronger than the characteristic auto ionized ion of the solvent will be levered off by the solvent, whereas the acid or base is weaker than the autoionized produce of the solvent remain in equilibrium. A proto solvent which are neither strong proton donor nor strong proton acceptor may act as a differentiating solvent for acid and base. Thank you.